In the last lecture, we had looked at the life cycle of a production system, and we had identified the major decisions to be taken during the life cycle of a production system. In this particular lecture, we are going to talk about the role of models in decision making. We will have a glimpse of different kinds of models that are used in practical decision making at various stages in the life of a production system. And the basic idea therefore is that to take any decision optimally, you quite often need to make a model of the situation and use this model for deriving what appropriate decision ought to be taken. So, in this particular lecture, we will deal with some of these issues. We will talk about what is a model, we will talk about the relevance to decision makers of various kinds of models, we will talk about different kinds of models which are useful, and we will give some example of how models help in real life decision making. So, that is the intent of this particular session. Here is a working definition of a model. A model is an abstraction to some degree of the real life thing or process for which we want to predict performance in a most general sense. The question that arises naturally is, what are the features of models and why do we make models? So, one must understand that models provide a focus on relevant factors and variables, which means if you have to understand reality, you must be able to pick out the relevant from the irrelevant, and by making a model you are essentially doing that. So, they help us in understanding reality and in picking up the right kind of factors and using them to express the relationships that we are interested in. Then models provide an opportunity for experimentation without undue cost and hazard. This is a major advantage of using models in production management. For instance, you might be using what are known as location models. So, you might want to investigate what is the effect of shifting the plant from Delhi to Bombay, from Bombay to Chennai in terms of costs. Now, if you actually started doing that, you would ruin all your assets. So, models help us in making this analysis without undue cost or hazard and help in maybe choosing the right location and things of that nature. And a third major feature of models is that they help in prediction of real life phenomena. There are a lot of uncertainties in the real world. The production manager has to deal with varying demands, for instance. All that he has access to perhaps is the past historical data. He might want to use the past historical data to find out what is likely to be the demand for the next period, so that he can plan the production of his product, which might be automobiles, for the next month. So, in that sense, prediction is something very important for a manager. The phenomenon which is to be predicted can be predicted by using a model. So, in this diagram actually summarizes the process by which you would make a model. What would happen is that there is the real world which you are interested in studying or capturing, and in order to study the real world you might have to use your judgment and experience and on the basis of these two things you come up with a model, and this model is then used for purposes of predicting performance of the real life system. And if the performance is okay, you continue using the model. If not, you have to revise the model. The revision of the model could generally take place either in terms of simplifying some assumptions or introducing some additional complexities into the model and so on. So, which again refines your judgment and experience, and this is then an ongoing process which helps you to make models, refine models and use them for purposes of decision making, because our intent here is to see how models are useful for decision making. Of course, for a model to be reliable, model validation is necessary, which means the kinds of results that you get from the model, are they actually coming out in conformity with what real results are, and this process is known as model validation. There are various mathematical ways of doing it, but essentially we are trying to find out whether the results from the model are good enough or not. There could be a variety of models. For instance, models could be physical. Some examples of models are a wind tunnel, and blade. You know, a wind tunnel is used to find out what the shape of the aerofoil should be, and therefore you can do various kinds of experiments to design the aerofoil. In that sense, it's a model, it's a physical model. Or a planetarium, which is a model of the universe, which will talk about the global structure. Or you would talk about the architect's model of building design, which is again a physical model. The major advantage of physical models is that they help you understand and appreciate how the whole would look together, and can therefore help you in forming some opinions or making some decisions. Models could be graphic, such as the representation of variables in 2 or 3 dimensional space, such as the history of demand plotted versus time, population, food production, traffic intensity. So, all such important graphs are graphic models which give you some idea of how the variable of interest is actually participating. The variables could be pictorial. I mean, the models could be pictorial. You can use visual pictures or cartoons or road signs. Road signs are also nothing but pictorial models which tell you that you can only turn right, or you cannot have a U-turn, or you have various other kind of things. Those are examples of pictorial models. Or a model may be a schematic, which means like an organization chart with authority relationships, information flow or current flow. All these kinds of models are essentially schematic models of the whole thing. Or there could be models which are mathematical. Essentially, mathematical models are those models where symbols are used to represent real life situations. You might want to represent the pressure by a variable P, the volume by a variable V, and depending upon the situation, you might say PV is equal to constant, or PV to the power eta is equal to constant. That is in fact a mathematical model of that particular situation of how gases behave. Or you could set up a simulation model. A simulation model is essentially an approximation of the real world, generally carried out with a high speed computer. So, you try to find out how the system would behave under varying conditions, and you try to simulate those conditions, and from those simulations you can draw some meaningful conclusions. That is the intention. So, these are some of the varieties of models that are there. By and large, if you look at this variety of models, you could classify these models in 3 different categories. And especially when we talk about models for decision making, it is convenient to talk about models as iconic or analog or symbolic, as the case may be. So, this is a classification essentially based on structure of the model. What we are saying here is, after all, what is an iconic model? When we are talking about iconic models, these are actually scaled up or scaled down versions of reality. To give you an example, for instance, a typical globe of the world is a model. It is an iconic model of the world. True, it has many simplifications, but it performs many useful functions. For instance, you can use this model to understand how day and night are formed, and with a little bit of ingenuity, you can also show how various eclipses are formed and understand how eclipses are formed. So, in that sense, these kinds of models help us in this. Nothing but a scaled up, or this is a scaled down version. There could be a scaled up version of reality. If you are talking about the molecular structure of, let us say, carbon, for instance, as a tetrahedron, and you want to put a carbon atom at every node of the tetrahedron, you can have a physical model which does this, and which can then help you probably calculate variety of atomic, interatomic properties that you might be interested in doing at that stage. So, remember that iconic models are just scaled up or scaled down versions of reality, and they give us an understanding, but the major problem with these models for decision making is that they are not robust enough. You cannot keep on changing the model parameters, because you will have to construct a new globe and a new model of the atom every time, and therefore their usage for decision making is limited. The second kind of model class that we talk about is an analog model. An analog is something where you substitute one property of interest by another. That is what it is. So, you have mechanical and electrical analogs which would try to simulate or substitute the system under consideration, and you have a very interesting example of this was a model developed by the London School of Economics, which talked about representing the entire economic world of different countries by a system of pistons and cylinders with water in between, and these piston cylinders were of different diameters, and they were connected depending upon the relationships of the individual countries in the world. The basic advantage of this was that if a particular country, major country like the United States, did a policy change, it was like moving a big piston, and its effect would be felt in all the other countries by moving their respective small pistons and so on. This is an analog, right? It is an example of what we mean by an analog. Then we have the symbolic model, which is essentially based on the structure where we are using mathematical symbols to represent relations. In fact, this is the most commonly used model in production systems, and in fact in almost all areas of project and production management. So, what we are doing here is that the quantities of interest are represented by some kind of symbols, and you establish the relationships between these symbols, you establish what your priorities and objectives are, and you have a mathematical model which tries to capture this situation. And some typical examples are linear programming, non-linear programming, queuing theory, inventory theory. All these are basically symbolic models. The basic advantage of using symbolic models is that they are the most robust. If anything changes, all that changes is a value for a particular variable or a parameter, and it is very easy to run the model again with these revised changes. You do not have to make a new globe or nothing of that kind. So, these models are essentially very, very robust. Based on the purpose, we can classify models into descriptive and prescriptive. Descriptive models are those models which merely describe the system. this is what will happen if you do this. Say a typical example, all queuing models are essentially descriptive models. They say that if this is the arrival rate and this is the service rate and this is the queue discipline, then the average queue length will be such and such thing, or something will be such and such thing, and so on. That is a descriptive model. A linear programming model is a prescriptive model. It tells you what should be the different quantities that you should produce so as to maximize your profit. So the production manager gets a prescription. He knows how much to produce each month to maximize his profit in that sense. But both are useful, and both can be, I mean, descriptive models can often be used to choose the right decisions. If you compare different decisions in a queuing situation, you can always find out, right. For instance, if you were to find out at a traffic light what should be the duration that the traffic light should be on or off in a simple traffic light, and you collect distribution of the arriving cars and other vehicles and so on, and suppose you do this exercise for, let us say, keeping a stoppage time of 2 minutes and then 3 minutes and then 4 minutes in your computer when you are doing this, then for each case you would get different amount, say average waiting times for the customers of waiting cars or whatever. So based on this, you would probably like to say, okay, I wouldn't like the cars to wait for more than maybe 5 minutes, and therefore I should have a stopping time of such and such. So in that sense, a descriptive model is being used for a prescriptive purpose in that sense of the term. Now, models can also be classified based on the environment. We are talking here about the decision environment. So broadly speaking, you can deal with what are known as deterministic models when you are assuming certainty for the various variables, or you are assuming a probabilistic model where randomness is assumed and some kind of variation is assumed for different types of variables. Since the symbolic models are generally the most popular in production management, we just look at a few examples of symbolic models. For instance, what happens is, as I said, if I have the past history, January, February, March, April, May, June, I have the actual demand for a certain product like this, and I want to utilize this information to find out what the demands for the future months is going to be. One very simple example is using a regression model or a forecasting model of the regression type, which is essentially a descriptive model. So you fit some function to this. It need not necessarily be only a linear function, it could be any function. And then once you fitted this function then behaves as a model which will tell you how much demand would be there for the future months. And depending upon the accuracy or the model validation process, you could rely on this information to take decisions pertaining to your production system. Here is an example from inventory. You are all familiar with inventory, and when we talk about inventory management, the classical problem there is that if I place an order for an item, the stock level suddenly rises and then it tends to fall gradually at an average rate. Actually, the actual fall might be might not be smooth in this fashion, but this could be this is one of the features of approximation that we bring about in the model. And then we say the average rate of consumption of this particular material is so much, and then again the new order is placed here, and then you get the supply here, so the stock level rises and so on. So the pattern of variation of inventory typically could be modeled as a sawtooth curve, which you know, and from this, by using a bit of mathematical jugglery, which I am not going to go into at the moment because I am trying to discuss the basic philosophy behind models, you get the economic order quantity is 2 into demand into the ordering cost divided by I, which is the interest rate, into C and under root. So you can get the optimal ordering quantity. So it becomes a prescriptive model. It prescribes for management what they should be ordering to minimize the overall cost in that sense. And once you have this information, you can in fact see how your the two major types of costs involved are the carrying costs. The carrying cost is the cost of keeping the inventory in stock, which would typically be, say, the average inventory level is Q by 2 into I is the interest rate into the C, which is the item cost. So you have a straight line variation for the cost here, and the ordering cost per annum is C0D by Q. So this particular function would be something like this. So what really happens is that you have two conflicting cost parameters, one increasing, one decreasing at a different rate, and the total cost would be something of this nature, and the EOQ is the quantity which minimizes the total cost. But apart from this, the model tells you a lot of other useful things. For instance, you might not be able to operate at the EOQ, but you can immediately find out that if you deviate from the EOQ, what is going to be the cost penalty that you are likely to pay? Is it better to shift in this direction or in this direction? And if I operate at a non-optimal value, how much cost am I incurring on these things? These are all important questions, managerial issues, which can be answered even through a very simplified model like the inventory cost. We can look at other examples of models which are very relevant in production management. We can use linear programming, non-linear programming, goal programming, models of different types of production processes, and we can model production product mix and scheduling by using these kinds of models. Now we will take a small example, for instance, and see how modeling for that particular product is done. Take a simple manufacturing problem. Let's say that the company produces two kinds of products. These products are simply desks and tables, and the manufacture of either desk or table requires 1 hour of production capacity in the plant. So whether you produce a desk or a table, it means 1 hour of production capacity in the plant, and the maximum available production capacity is only 10 hours per week, let's say, and there is a limited sales capacity. You can sell at most 6 desks per week or 8 tables per week in that sense, and the gross margin of profit from the sale of the desk is 80 rupees and from the sale of a table is 40 rupees. So if we want to model this situation, actually this is a very important prototype occurring in industry. It's the product mix problem, right? You companies always make a number of different products, so you are trying to find out what should be the optimal product mix. So let's suppose that the priority wise goals of the company are: the management wants to avoid any underutilization of production capacity, that's the first goal. The management wants to sell as many desks and tables as possible, but since the gross margin from the sale of a desk is twice that of a table, there is twice as much desire to achieve sales goal for desks as for tables, which is quite obvious. And the third one is management desire to minimize the overtime production of the plant as much as possible. So if you want to work with these priorities, what can happen is, well, incidentally, you can solve this problem graphically, and what we see here is, if on the x axis we have the number of desks, which is x1, and on the y axis we have the number of tables, which is x2, then what we have basically is the total sales capacity for tables is this line. You can't sell more than 8, you can't sell more than 6 of desks, so you have this line here, and the ideal production capacity which you have utilized both, because each capacity you have 10 hours of available, so 1 hour on each. So this would be just a line here with this intercept 10 and 10 on both sides. So what you find is that if you were to solve this problem as a linear programming problem, the space shown here A, B, D, E, O would be the feasible region as far as the desks and tables are concerned. So, you have this information. This itself is useful as to what can be the range of products that you can make. You cannot make, for instance, so many tables or so many tables which are outside this, that itself. So, it gives you the feasibility range in that sense. And then of course, if you work out the profits at all the corners, you find that the maximum profit would in fact, if we confine ourselves to only the points A, B, D, E, O and exclude C, which currently is not feasible, then of course you will find that the point D gives us the maximum profit of 640 in that sense. But now if you impose the priorities which we had decided for this particular problem, you will notice some interesting things. So, what would happen is that if we said, for instance, look at this example, if you do not want to this line here, this line shows that you are utilizing your capacity fully, and if you go in this direction, you are basically trying to overutilize your capacity, and if you come in this direction, you are underutilizing your capacity. So, in that sense, since the priority said that we do not want to underutilize our capacity, that means there is no implicit bar on overutilizing the capacity either through overtime or through subcontracting or whatever. In that case, point C would become your the point which would have, for the stated priorities, the point which is the best solution. And at this particular stage, the first two goals are not achieved, the third goal also is not achieved, and therefore, since the overtime at this stage is 4 hours. So, what can happen is that you can keep on changing the sequence of priorities and investigate if the solution changes. That is something that you can do. And in fact, what we are talking about here is a variation of linear programming, typically known as goal programming, in which we define a goal and then we talk about the deviations from the goal, and we are then looking for solutions within a certain priority. So, this would be the way in which a goal program would look at this particular solution. And when you look at a formal definition of goal programming for the problem, it would in fact be something like this. You have the number of desks and the number of the number of tables as the two variables for the problem. We define an overtime operation, if any. So, there is a D1 plus, D1 minus is the idle time when the production does not exhaust capacity. So, this is the sales restriction, x1 is less than 6, x2 is less than 8, or we can introduce here, this is like a slack variable. So, D2 minus would be the undertime capacity. So, this is equal to 6 here, and this would be equal to 8. So, we have converted these two inequations into two kind of goals using these deviational variables D2 minus and D3 minus. And what we can then do is, we have a capacity constraint, and the capacity constraint reads like this: x1 plus x2 must be generally equal to 10, but we could be producing less than 10, in which case this variable will come into operation, or we could be producing more than 10, in which case this variable would come into operation. So, since we can operate anywhere, we can have both these variables coming into play. So, this is like the interpretation of this can be that this is a target and these are the under deviation and the over deviation from the target, because you do not know to begin with whether we would be under deviating or over deviating from the target. So, it is a very convenient device to model such situations. And then of course, the objective function now would have 3 priorities based on the priorities that we had: minimize the underutilization of the production capacity, which is D1 minus production capacity. This was 2 times the deviation from because the profits from the desks and tables were different in the ratio of 2:1. So, you have this particular goal here, you are minimizing this deviation, and the third priority is to minimize D1 plus, which is minimizing the over capacity, that is overutilization of capacity here. So, this solution would lead to point C that we saw as the optimum solution. And finally, this model would actually be set down in this form, and you can use a goal programming code to set it up. Notice that we have basically deviational variables and constraints in this problem, and the objective function is in the nature of the priorities and the deviational variables. That is what happens, right. So, this is a very common type of form which is used here. Now, let us look at a simple linear product mix problem, which is product mix in the sense that if we generalize this, we were talking of a situation where we have only 2 products. Now, we have n products. Okay. So, the n products are indexed from I is equal to 1 to n. So, this is the third variation that we are talking about, a simple linear programming in 2 variables, a goal programming problem in 2 variables, just to indicate to you that when you have multiple goals and conflicting priorities, you use that situation, okay, goal programming. And this is a generalization of the first model. You have m resources, Aij is the consumption of the jth resource per unit production of the ith resource, Bj is the availability of the jth resource in general, and Pi is the profit contribution per unit of the ith product. So, when you have this, the various other variables are, the notation is Ui is the upper limit on sales of the ith product, Li is the lower limit on sales of the ith product in general, and Xi is the production of the ith product in the planning horizon. So, this is our decision variable. You want to find out how much of each quantity to produce, and typically you have this situation. This model would actually look like this. The objective is to maximize the profit. So, P1 is the profit per unit from each unit of the first product. So, P1 x1 plus P2 x2 and so on up to Pn xn is the total profit that you earn, subject to various constraints. And these constraints, if you see, are each right hand side here is a resource availability, and this is the resource consumption. This is the resource consumption by the first product, resource consumption by the second. So, if you are talking about labor hours, say my labor hours are 10,000, 1 unit of the first product consumes 5 labor hours, this consumes 10 labor hours and so on. So, this would be then the consumption in terms of labor hours. So, all that we are saying is total labor hours less than this. So, this could be the consumption of money, this could be consumption of space and so on. So, whatever the resources you have, the m resources, it is a generalized model for a product mix, and it is a model which can be very useful to handle the LP problem. Now, then of course, you would have restrictions on sales. Xi should be less than some upper bound, less than equal to from some upper bound and greater than equal to some lower bound. The upper bound could be the total capacity, or rather it is the demand. So, it would be the total demand for this product, and the lower bound would be some minimum amount that you would have stipulated or contracted to make for that particular product. So, that is Li. Then this model would easily be solved by an LP code. Notice that I am not talking about solution procedures here. Solution procedures are generally simple, because you have access to available codes, you can solve them easily. What is the primary role of a production manager is to model a situation and set up a appropriate model for his factory or his situation or whatever it is, and then that model can be solved very easily. So, let me just now make a digression to a model of the economy as a whole. You see, we have looked at variants of linear programming, a simple 2 product linear programming problem, a simple 2 product goal programming problem, and a n product multiple product mix problem in general. Now, those were all instances of models which were actually trying to solve problems which are generally encountered within the factory, And all the examples that we were talking about were of that nature. We talked about the forecasting model, developing the demand. Then we talked about the inventory model, setting production targets or setting ordering targets for individual products within a factory. And then we talked about the product mix, which is also a decision within the factory, and so on. So, in order to develop a broader perspective of the role of models in production systems, we will look at this Leontief's input output model, which is actually a macro model of the national economy. After all, the economy is also a production system. It is producing different kinds of products, and we will consider a number of interacting industries within the economy, and the applications of this model include integrated planning for the whole economy, which means, for instance, whenever the planning commission wants to make the next 5-year plan for your country, how does it do it? Well, the Leontief's input output model is the basis for doing it. So, we will see exactly how this planning can be done. You set the targets for individual industries. So, this also comes out. The targets would be that agriculture sector should be given so much, and this is their target production for the next 5 years or whatever it is. Resource allocation to various sectors is also possible through this kind of a situation, and price prediction and control in the economy is also possible. Now, you might be a little flabbergasted by saying how so many things can be done by a simple mathematical model. So, let us look at the basics of the Leontief's input output model and see how exactly we can go about looking at this particular problem. So, some of the assumptions in this model are: the major assumption is that the economy consists of a number of interacting industries. Would you tend to agree with this or not? What does this mean in real life? It means, for instance, that if you talk about a particular sector in the economy, let us say you talk about automobiles, for its survival, automobiles will have to borrow from the steel sector, the steel. It will probably have to borrow from the engineering sector, different components and so on, which are going to be used in the automobile sector. And then, of course, all these things are going to be put together, and there must be a demand for automobiles. So, you have people from different sectors who are actually going to use those automobiles. So, the important thing really is that, in fact, this is the key feature of Leontief's model, that it tries to model the interactions that take place between the various industries. Now, one assumption that is made here is that each industry produces a single good and uses only one process of production to make this good. For instance, one might say that if I divide the economy into various sectors, and let us say automobile sector is one of them, then for purposes of macro planning, I would not say that the automobile sector produces cars, jeeps, two-wheelers, three-wheelers and so on, which are all different kind of items, right, but they are all automobiles. So, I could club them together, and I probably say that the output of the automobile sector is in terms of general automobiles. However, if you want, you might be able to say work in terms of standard passenger units, which says that the Maruti 800, for instance, might be taken as a 0.8 standard passenger unit. A Maruti 1000 might be taken as a 1 standard passenger unit. Bigger cars might be taken as 1.2, 1.5 standard passenger units. So, that would give you a basis for aggregation, or you might work in financial units, and then everything gets combined very easily. Normally, in the Leontief's input output model, we tend to work with financial units. Okay. So, this is what we mean by saying that it produces a single good It does not mean that automobile what produces a single good, that single good is automobile, and each automobile would be different, could be different. So, each industry produces to satisfy the demand in all other industries apart from an exogenous demand. Under these assumptions, we will try to see what exactly we. So, the interaction between various industries in the economy. So, we are now looking at the economy as a whole, right. And we have these various industries which are interacting with each other. That means there is a two-way interaction, something can flow from here to here, something can flow from here to there, etc., and there are various possibilities and so on. So, we have industry 1, 2, 3 and so on up to n, and let us look at some two industries. Let us call this as industry I and let us call this as industry J, just to understand the notation which we shall be using for this particular model. So, n is the total number of industries which is there. Yij is the amount of good I needed by industry J. So, Yij is flowing from the ith industry to the jth industry, because the jth industry during the whole year or during the whole period, mind you, this entire exercise is for a certain period and normal period is 1 year. So, Yij is the amount of good I flowing to industry J in that particular period and so on, and Bi is the exogenous demand of good I. So, every industry will have some exogenous demand which is either exports or whatever the consumers consume, that is the exogenous demand. So, this is the model that we are trying to look at in terms of Leontief's model. What we find here is that there are two types of things that we can do. First of all, our intention is to find out what is the production of each of these individual industries, number one, and the second objective is to find out what would be the prices prevailing in the economy. These two things which Leontief's model gives us. So, if you look at this, we can apply a simple mass balance equation. Mass balance equation, for instance, would be the total amount Xi which industry I must produce to exactly meet the demands is Xi equal to summation Yij plus Bi. Bi is the exogenous demand and Yij is the amount which is going to industry J. So, this particular summation that we are talking about here would be summation over all J, right. So, you know, for instance, this should be J here. The total amount flowing from I to all other industries plus Bi should be equal to what is production for that. It is a simple mass balance equation. This is like in electrical engineering, this would be something like Kirchhoff's current law. Okay. Then the notion or the sort of approach that Leontief took was that he developed what are called production functions. Now, what is a production function? If this is industry I and this is industry J and industry I is supplying a quantity Yij to industry J and industry J is producing a quantity Xj, let us say. What does it mean? We say we relate the inputs Yij to the output Xj of each industry J. So, how do we do it? We simply have to say that Yij is equal to Aij into Xj for all Ij possibilities. All that this is saying is in any industry there are multiple inputs from different sources. So Yij, that is the amount of input I required for producing a unit of j, is equal to Aij in that sense of the term. Okay. So what it implies really is something like this. So what is the significance of this Aij? So Aij would in fact be, you can see from this equation, Yij divided by Xj would be Aij, and Aij would then have the interpretation of the number of goods I needed to make one unit of good j. If this sounds a little complicated, let us take a humorous example. The example is very simple. He says, suppose this industry makes cakes, or makes a cake, or baking a cake, which you probably your mother does at home. Okay. So if you want to make a cake, what are the various inputs you have for making cake? You would need mainly maida, you would need baking powder, you would need sugar, you would need other inputs depending upon the kind of make, the kind of flavor you want to give to the cake. Okay. So the idea is that to make the cake you have this. So the point really is that if I want to make a 1 kg cake, so I would probably use 750 grams of maida. The point that is being raised here is that if I want to make 1 kg cake, that means if I want 1 kg cake I need 750 grams of maida, and I would probably need a pinch of baking powder. Okay. If I make 2 kg cake, what would you need? You would require 2 into 750, that is 1.5 kg maida and 2 pinches of baking powder and various other things. So it is exactly in that same spirit that we are relating the inputs to the outputs here. And what we can then say is that this Aij, if you plot the relationship between Yij and Xj, we have said Yij is equal to Aij Xj, so this would be a straight line whose slope is Aij. So Aijs are known as the input output coefficients or the technological coefficients, and here we are assuming linearity, we are not assuming any economies or diseconomies of scale. It is a static situation in which the Aij is constant, and if it is a dynamic situation then Aij would be allowed to vary. That is what we are trying to say. So what is really happening is, keeping the example of the cake in mind, if you want to find out or predict the total requirements of a certain industry, it will depend, it will be a fixed proportion. If I want 2 kg of cake, I use 2 into 750 grams of maida in that sense, same sense. So similarly, if I need to produce 1 ton of something, I need this much of input. If I double my output, then I would require more of input, and this Aij will actually capture how much of the input you would require. Okay. So this is the technology coefficient. So the basic production model in this particular situation comes out like this: x1 would be equal to this particular thing which is there plus b1, right, by mass balance equations. X2 would be again a similar equation, xn would be a similar equation. So if you put it in matrix notation, you get x is equal to ax plus b, and then you can directly solve these equations for x's, and you get x is equal to I minus a inverse b. This is the basic Leon-Teefs model. What it says is that you can now calculate the production quantities knowing the requirements of the individual sectors in the economy if you know the technological coefficients, that is the matrix A. So this equation is a the fundamental equation which is used for solving this particular problem of determining the production quantities as a function of the you can say the these are the exogenous demands. So knowing the what does the planning commission do basically? The planning commission says it finds out by talking to different sectors as to what is likely to be the demand in the next 5 years. So, different people converse and they generate the vector B, and once the vector B is known and assuming that the input output coefficients remain unchanged, you can calculate what the production target should be. That is it. That is the basic idea of the basic production model. The second aspect of this model is the prices in the Leontief system. The prices in the Leontief system, if Pj is the unit price of good J, then Aij Pi would be the cost of the Aij units of good I required to make 1 unit of good J. Simple. And therefore, the cost of goods 1, 2, 3 and so on up to n needed to make 1 unit of good J would be the summation of this. So, we have summation from I is equal to 1 to n of Aij Pi, and if the value added in the industry, now value added is important because each industry is adding value. That means the total cost is 20 rupees, it is making a profit of 10 rupees and selling for 30 rupees, that is the idea. So, if Rj is the value added in the economy, so price of good J minus this quantity should be equal to the value added in the industry, and basically these equations for I is equal to 1 to n will also be the n equations that you will use to solve Pj's. And what happens is, if you write them in matrix notation, you get I minus A transpose into P is equal to R. That is what this equation basically leads to, and therefore P can be written as I minus A inverse transpose with multiplied with R. This is the value added, and this is the price model. So, together the price model and the production model constitute the basic Leontief structure. This was the production model which we studied a short while ago, in which you are calculating the production quantities as a function of the exogenous demands B of the products. Now, here you are calculating, knowing the value added, you are calculating the prices in the economy. So, you can calculate the prices in the economy, and the beautiful discovery of this particular model, for which Leontief got the Nobel Prize incidentally, was that here you do not have to do additional effort to calculate this, because this is I minus A inverse which you calculate once. This is just I minus A inverse, the transpose of that. So, it is the same, the inverse is automatically calculated, you do not have to do any matrix inversion again. And in fact, it was this particular discovery that led to the difference between primal problem and dual problem in linear programming, and it was about the same time that George Dantzig was working on the simplex method of solving the linear program. This was in the early 50s that Leontief discovered that this is another way of looking at duality, and therefore, in this A is the matrix of technological coefficients that we have just now seen. P is the price vector. So, this is the prices which prevail in the economy. What is the cost per unit in the automobile sector, in the agriculture sector, in the labor sector, etc. So, those prices, and those are determined by this model. R is the value added vector. You see, what can be done, for instance, by the government is, in planning, they can give more subsidies to certain sections of the economy, which means that they are playing with the value added vector of that sector. So, if you add to the value added vector of that particular sector, for instance, if the government gives concessions to the agriculture sector and you know how much concessions are being given, you can calculate immediately what is going to be the impact of this concession on the overall pricing in the economy for the different sectors. That, I think, is a very, very useful way of interpreting the. So, ultimately we have, so this was intended to give you an idea of the price model as well as the production model of Leontief, which can be utilized for solving this.
How is the R vector calculated, sir? The internal cost of the company?
No, the R vector is the value added for the economy. Now, value added for the economy is actually governed by the competitive situation in the market. precisely, isn't it? How much value can a textile guy have, how much value can an automobile value have for his product? It is determined to a very large extent by those particular dealers. That is one of the things. And then this could be something that they would decide to set, it is their decision. If I make a product and make it for 100 rupees and decide to sell it for 150 rupees, so I have actually set my value added in that sense of the term. So value added to a large extent is the amount of is what the particular industry expects from its product in that sense. So you will supply the value added vector and then compute the prices. I mean, it will be like this, that if we add the value added or keep the value added, we would try to work out this particular situation, right. Finally, let us summarize what we have tried to do in this class. We have tried to look at the purpose and types of models that are there for decision making, and the basic theme was that all these models aid decision making in the production management situations. We took some examples of models. We look at a forecasting model, a lot sizing model, a product mix model for graphic and LP, and also an example of a macro model like a Leontief input output model, which helps us take. It would not be wrong to say that the study of production management is basically a study of models of different kinds, and these models, once you carry in your bag, you apply for real life situations. Thank you.